zero-order reactions. So zero-order reactions. And in a zero-order reaction, the characteristic is that we have a rate. So we might have a reaction where A is consumed. And this rate equals just simply minus because it's consumed. And the consumption is constant, minus K. So this K is the rate constant. And this particular rate in a zero-order reaction does not depend on how much of the A we have at a given time. It's just always a constant. And I think what I haven't given you is the explicit equation for to solve a zero-order reaction. And in this case, the equation is A at the time t minus A at the time 0 when we start the observation equals minus K times t at the time t minus t when we start our observation. So that is the equation for a zero-order reaction. And ideally for an exam where it's not open book, I want you to remember this. You can, of course, rearrange this equation where you say basically A at the time t equals minus K times t. Usually you would just write it as t plus A0, and you see that this is the equation of a straight line. So y equals mx plus c. And if you were to plot this, what you could do is you could plot the concentration of A versus time. And what you would see is something like that, straight line. When we reach 0, usually you can't go below 0 when we are talking about a concentration. So this would then probably look like something like this. Yeah? This point here, obviously, that's our intercept with the y-axis. That would be our A0 at our starting point. And the gradient of the whole thing, that is our minus K. Minus indicates that the line goes up or down? Down, exactly. So this one here is minus K. And please note, K is always larger or the same as 0. You can't have a negative K. Okay? That is for a zero-order reaction. I've given you some examples for zero-order reactions. That would be the elimination of, let's say, alcohol from the male body. Females have a slightly different elimination profile. Nobody really knows why. This would also be the reaction when you're looking at enzymes at very high substrate concentrations. You have done enzymes, or you're currently doing enzymes, right? So when you have a Michaelis-Menten plot, which you, by the way, you should never ever use a Michaelis-Menten plot. Has somebody told you that? Huh? No? You don't know why you shouldn't use a Michaelis-Menten plot? Ah. What do you plot in an enzyme reaction? You plot substrate concentration, right, versus the rate. True that? So, what you see is, usually, you would get something like that. Right? And from this plot, you're trying to get a Vmax. Yeah? You've heard about Vmax. You need the Vmax to get Km. Yeah? You've heard about that? Because Km is defined as the substrate concentration where you have half of the maximum velocity. Okay, so if you've got something like that, what is your Vmax? Is this point actually Vmax? No. Where is it? It's the asymptote. Yes, you're absolutely right. So where's the asymptote?
So it approaches the maximum point.
Yeah, but where is it here?
Well, it's not.
So it could be here, right? It could be here. It's complete guesswork, right? So that is why you want to do a completely different graph. That is why you want to never use a Michaelis-Menten plot. Because in a Michaelis-Menten plot, you don't get any chance to interpolate. That is why you transform the Michaelis-Menten equation into something that is linear. And you can do that either with a Lineweaver-Burk plot, which is okay, or still pretty crap, or you can use what is called the Eddy-Hofstee plot. Have you done that? No? And an Eddy-Hofstee plot, actually I shouldn't do enzymes, should I? It's confusing. So the Eddy-Hofstee plot, what you do is you plot rate versus rate over the substrate concentration. What you get in an Eddy-Hofstee plot is a straight line. This one gives you Vmax. This point here gives you Vmax over Km. And the gradient gives you minus Km. It's the best plot that you can use. Eddy-Hofstee plot. Google it. It's on my YouTube channel, by the way. Okay. Now, when you look at a Michaelis-Menten plot, what you see is that when you are in this range here, in the asymptote, you will find that will the rate increase? Will this rate increase when I increase the substrate concentration? When I go up with the substrate concentration, will the rate increase? Yes or yes? No, it won't. The rate is a constant. Yeah? And it doesn't matter then if I add more substrate, the rate stays constant. Constant high. Because in this case, all the active sites of the enzyme are occupied. Yeah? So what you are reaching here is a state where the rate is no longer dependent on the substrate concentration. So you are in a region where you have a zero order. Yeah? In the enzymes. Now, when you look at the rate here, for example, right at the beginning of your enzyme reaction, where you have very little substrate concentration, does the rate in this range here, does the rate depend on the substrate concentration? Or in other words, what happens if I increase the substrate concentration? Does this have an effect on the rate? I increase from here to here, from here to here. Does that change the rate? It changes the rate dramatically, namely from here to here. Yeah? So when I increase the substrate concentration, the rate also increases. In this case, what you are dealing with here, in this particular case, is you're dealing with a first-order reaction. So you have a first order, and it continuously changes and goes into a zero order. This is the weird thing about an enzyme reaction, that it doesn't have a defined order. The order of an enzyme reaction actually depends on the substrate concentration. Usually you find reactions that are either first order or second order or 1.5 order or 0.3 order or something like that. Enzyme reaction, the order changes continuously, which is a right bitch. Anyway, I just wanted to show you that we have a zero order when we have lots of substrate, and we have a first order reaction when we have diddly squads of substrate. Now let's have a look at zero order, at first order reactions. Again, we have a substrate or reaction where we have an A, that's our substrate or reactant, and that is consumed. And we can write the general rate equation. So rate equals minus, because it's consumed. Okay, that's the rate constant, times the concentration of A to the power of 1, if you like. So this 1 is the rate order. I told you rate order can be anything. In contrast to the molecularity of a reaction, molecularity can only be 1 or 2. And I think I gave you the equation for that, the explicit equation. And the explicit equation for that is ln of A at the time t minus ln of A when we start the observation equals minus k times t at the time t that we are interested minus t when we observe it. The only difference between this equation and the equation for the zero order reaction is that you have ln's, that you have an ln here and an ln here. Yeah? But this is a massive. difference. Now for some applications this equation is good. For other applications this equation is oh. And we can play with this equation a little bit. We can simplify it. That's why we have done, right at the beginning of last term, we have done a little bit about ln's and logarithms. Remember? Vaguely. And we said something like that can be simplified to ln of at divided by a0. So we, should be an a, sorry. At over a0. So you would have to calculate At, the concentration when we are interested in it, divided by our starting concentration, and then form the ln of that, equals minus k tt minus t0. So this equation here is the same as this equation, just a little bit simplified. How do we get rid of an ln? To the power of e, exactly. Now let's do that with this one here as well. Let's do it to the power of e. So we get, and let me do that, let me write this down here again. ln at over a0 equals minus k times t minus t0. We take both sides to the power of e. E and ln are the inverse operations. And we get basically e and e. Yeah? E and ln, what happens to them? They cancel each other out. So we've got at over a0 equals e to the power of minus k times tt minus t0. Make sense? Or if I'm looking for at, all I need to do is multiply both sides by a0, and I get at equals a0 times e to the minus k times tt minus t0. Yeah? So I haven't done anything, hopefully I haven't done anything illegal mathematically or weird or something like that. But I have now 3 equations. It's better than Aldi. It is 3 for the price of 1. This is our starting equation. This is an equation that follows. And this is our third equation. So you actually have to learn only one equation as long as you can do the mathematical transformation with the e and things like that. Yeah? Does it make sense? So you only need to learn one equation. I usually go for this equation here, or rather this one here, because then the rest follows. Yeah? So that's a first order equation. We also said that for a first order reaction, if we plot that, so if we plot concentration of A versus time, what do I get? Do I get a straight line? Remember? Do I get a straight line when I do that? Yeah? If I plot A versus time? What I actually will get is something like that. It will give me a curve, which is bad, because I just told you curves are not good. Unless you are Kim Kardashian or something like that, then curves are good. But not when you want to extrapolate anything. So what do we need to do? We need to convert that into something that gives us straight lines. Now, when we said we have ln A at the time t minus ln A at the time 0 equals minus k times basically the time here. All we need to do is we bring this to the other side here, and we get ln A at the time t equals minus k t plus ln A0. And again, you see this is the equation for a straight line. Y equals mx plus c. So if we now plot, instead of concentration of A, if we plot ln of A versus time, we get a straight line. This line goes from here. It can go into the negative range, so don't worry about it. This point here, obviously, is our starting point, ln A0, and the gradient is minus k. Yeah? Does that make sense? So, little question for you. I have a reaction. When I plot in this reaction, when I plot A versus time, and I get something like that. What order is it? Loud? It's a zero order. Why? Because it's a straight line. Yeah? We said for a zero order, if I plot a zero order A versus time, then I will get a straight line. Turned on its head, when I get a straight line, it must be a zero order in this case. Okay, I plot another reaction, A versus time, and I get something like that. What order is it? Sorry?
You can't really tell.
I can't tell, but what can I say that it's not?
Zero.
It's not a zero order, yeah? Definitely not. It could be any other order. Now, if I plot the same reaction, time, ln A, and I get something like that, what can I say? Sorry? Then I can say it's a first order reaction. Exactly, because it gives me a straight line. Yeah? Okay, let me quickly do this. What happens if I plot ln versus time. And I get something like that. Loud? I can say it's not a first order, right? It must be something else. So when I ask you to demonstrate that something is a first order, what do you need to do? I draw an ln versus time, and this should give me a straight line. And I can say, if it gives me a straight line, I know it's a first order reaction. Simples. One more thing, it's a little bit like Apple. One more thing about a first order reaction, which is specific for a first order reaction. It doesn't work with any other reaction. So there's a little bit of a health warning coming with that. For a first order reaction, let's say we have an A0, which let's say is 100, and an AT, which let's say is 50. So in this case, A0 is 2 times A at a certain time t. Yeah? I can write in my equation ln AT over A0 equals minus k times t minus t0. Yeah? Now I can put these things in. I can say, for example, ln 50 divided by 100 equals minus k times tt minus t0. $50 divided by 100 is 0.5. And 0.5 equals minus k tt minus t0. Do you know where it's going? Yeah? What is... I can write ln 0.5 in a slightly different format. I can write ln 0.5, I can write this as minus ln 2. Rules of logarithms. If you don't know it, don't worry too much about it. But I have now, if I go back, this one here. We said this is, can't write on that. So I can write it as minus ln 2 equals minus k times t. We ignore the 0 because that's the starting point where we start looking at things. The minus cancels out. And the t equals ln 2 divided by k. This t is actually the time it takes to go from 100 to 50. Yeah? From 100 to 50. To go from 1 to half. That's why this t is also called the half-life. Not low life, as I've seen it in an exam paper. People were probably referring to me. But it's half-life. And it's usually written as T half. And I want you to remember this equation. This equation basically gives us something about a relationship between the rate constant and the time of the reaction. Now, I said to you this reaction, this half-life, tells us how long it takes to go from 100 to 50. Yeah? Now here is a question for the specialists. How long does it take to go from 50 to 25? The same. This is again ln 2 over k. Yeah? Because it's the same thing. It's the same half. Okay, how long does it take from 25 to 12.5? It's the same. Again, ln 2 over k. Yeah? It only works for a first-order reaction. But it works. So you could argue that if you have a reaction and the half-lives are the same, this is indicative of a first-order reaction. So some people argue, when I give them a reaction, and I say, demonstrate graphically that this is a first-order reaction, instead of doing that, ln A versus time, where they get a straight line, that's the easy bit. Yeah? But what they do, and which is not wrong, I would say, but it's a little bit more complicated. What they do is they do an A versus time. They get something like that. And now they argue that, okay, the time going from here to here is this amount of time. Yeah? Now going from here to the next half, that's this one, that is this amount of time, and so on and so forth. So what they do is basically look at here the half-lives. And then they say the half-lives are the same, therefore I know it's a first-order reaction. It is, sorry, say again? It's a little, you're absolutely right. It's really, it's not wrong. But it's a little bit like the question, can you get syphilis on a private toilet, or on a public toilet? The answer is yes, but why so complicated? There are other ways to get STIs, right? So it is correct, but I wouldn't do it. At least not on a public toilet. Yeah, you know what I mean. So my advice is go for this one here. It's much easier, less painful, and you really don't have to do a lot. That make sense? So we have done zero order and first order. Actually, Is it worth doing this problem question, or shall I give you another one? Okay, give you another one. Give you another reaction. Not terribly common, but if you've got, for example, two receptors that are dimerizing, something like that, you have a typical reaction of this particular type. It is, you have rate equals minus K times A to the power of 2. What order is it? Right? It's a second order. It's a very special second order because your reactants are the same. What would happen if you had A plus B gives something? How would you write this as a rate expression? You would write this as rate equals minus K times A to the power of 1 times B to the power of 1. It is a first order with respect to A. It's a first order with respect to B. What's the overall rate order? It's a second order rate, but it's different from this one here. Yeah? You can solve this one, but oh boy, that is complicated. You have got logs and God knows what other horrible things in there. So I would not expect you to ever solve anything like that. However, this one here is actually not too bad. You can write the equation for that. And in this case, the equation to solve this for this A plus A, the equation for that is 1 over A t minus 1 over A0 equals positive K, that's just a quirk of the maths, times T, well, T minus T0. And again, you can convert that into a linear form. You can say 1 over AT equals K times T plus 1 over A0. And again, that is a linear equation, y equals mx plus c. Yeah? So, what do we plot? What do we plot on the y-axis? 1 over A, exactly. 1 over A versus time. And what does the graph then look like? Up or down? It goes up this time. It would start here, and it goes like that. This point here, that is this one, 1 over A starting point. And the gradient, in this case, is again our rate constant. So, question for you guys. I plot my reaction A versus time. And I get something like that. What is it? Not a zero-order reaction. Okay, next try. Next try would be ln, okay, ln A over time. What can I say? It's not a zero order, and it's not a first order reaction. Okay? Next try. Time 1 over A. I get that. So what do I know? It is a second order reaction with this particular type of A plus A. Yeah? What happens if I would get something like that? I know it's not a second order. That means either it is not a second order, or what could it be? What else could it be? It could be a second order, but it's not A plus A. That's right. Or you have messed up, or I have messed up and I've given you the wrong data. Not unheard of. Yeah? So I really want you to remind these three cases. What you would usually find if you look at a second order rate, when you plot A versus time, a second order rate usually would look like something like that. Very steep going down. But don't take it as gospel that when you see something like that as a second order, do the plot and see if this is the case indeed, if it gives you a straight line. Make sense? So, we've revised zero order, and I've given you the equation A at the time t minus A at the time 0 equals minus k times t. We've discussed the graph for that. We talked about the first order, and the new stuff that I showed you were the different equations that you can use for that. And we talked about the half-life. And this half-life can be useful. Very often what you find is, actually, last week I told you that the first order reaction is very common, or is the only reaction when you talk about radioactivity. So, very often in terms of radioactivity or nucleides, you have a given half-life. Nobody really talks about rate constants. So, for example, the half-life of 32 phosphorus, which is very commonly used in biology to label nucleic acids, the half-life is 14 days. So 14 days, that's the half-life, equals ln2, and this ln2 is always there, yeah? And this is 0.693 divided by k. That's the rate constant. Now you can easily rearrange this equation, and from this data you can calculate your rate constant. So k equals 0.693 divided by 14 days. Make sense? And with this k, you then can do all the other equations. Are you happy with that? Any questions? Go in peace, but go and have a good weekend.